Welcome to section 2.4 Sequences and Summations. We are using the text Discrete Mathematics and Its Applications by Kenneth H. Rosen. This is Dr. Gilbert Eyabi. Section Learning Objectives. Number 1, sequences. We would look at geometric progression or GP, arithmetic progression or AP. Then we shall look at recurrence relations, especially the Fibonacci sequence. Then we shall touch summations, probably in part 2 of this lecture, and then look at some special integer sequences. Let's begin. Introduction. Sequences are simply ordered lists of elements. For example, we have 1, 2, 3, 5, 8. If you look very carefully, you might be able to figure out some kind of pattern between these integers or these numbers or these elements. If you look at the second one, we have 1, 3, 9, 27, 81, and then I prefer the 3 dots, the ellipses, which means it continues in this pattern forever. So if I'm interested in the next term, what would that term be? I have to figure out, is there some kind of pattern between these elements? Can I discover the pattern? What if I'm looking for the 589th term? Do I have to list out all the elements before I can find that term? Or can I find a general formula that predicts each term? In that case, if I'm looking for the 697th term, I just plug 697 into the formula. We would observe that it is very easy to determine the formula. Sequences arise throughout mathematics, computer science, and in many other disciplines ranging from botany to music. So here we're going to introduce some terminologies. Definition, sequences. The good thing is we just dealt with functions in section 2.3, so it's easy for us to get functions in as we define sequences. A sequence is just a function f whose domain is the set of natural numbers union the number 0, and the codomain is the set of real numbers. You could just say the codomain is the set S, where S is a subset of the set of real numbers. I would just prefer to use the entire set of real numbers as my codomain. In other words, f of n would be defined as an. So the nth term of a sequence, or the n plus first term, depending on whether you are defining this sequence starting from 0. If you start from 0, then an is actually the n plus 1 term. And if you're starting from 1, then an is the nth term. But you shouldn't worry much about that confusion because I'll make it clear as we move on. But an is how we would define our sequence, and an would be the term in n. I'll prefer to call it that way instead of the nth term. Just call it the term in n, and that equals f of n. So f of 5 would be the same as a5. Okay, let's proceed and look at an example. Consider the sequence an. You see, this now is a sequence and not a term. So if I put it in braces in the set notation, that makes it a sequence. And if I write it out as an equals 1 over n, then that means the term in n, which in this case, because I'm starting from 1, this will be the nth term. The nth term is 1 over n. See, I'm starting from 1a, 1a to a3. I cannot have a0 because that would be 1 divided by 0, which makes life in mathematics very uncomfortable. We don't like dividing by 0. So we can say define an from n to r by an equals 1 over n, and then I can find the 25th term, which would just be 1 over 25. Now let's begin with a special class of sequences known as geometric progression. A geometric progression is a sequence of the form ar squared, ellipsis, ar to the n, ellipsis. So look at it very carefully and see what you observe. That is a to the r squared. Interesting. A is known as the initial term, and r is known as the common ratio. Let me go down here a little. So how do we define a geometric progression? A sequence is in a geometric progression if the term in n can be written as ar to the n. I'm starting from 0 in this case. So we have a0. A0 would happen when n equals 0. So r to the 0 is going to be 1. And so my first term, which will be a to the 0, is going to be a. And then the next terms. Now, I could also define a geometric progression of the form an equals ar to the n minus 1 if I'm going to start from 1. In that case, when n is 1, then 1 minus 1 is 0, r to the 0 is 1, and my first term, a to the 1, is going to be a. So the first term could either be a to the 0 or a to the 1. It all depends on whether I'm starting from 0 or I'm starting from 1, but that shouldn't be a problem because each question is going to make it very clear. Okay? Now, r is the common ratio. How do I get r? I simply divide consecutive terms. A2 divided by A1 must be the same as A3 divided by A2, must be the same as A4 divided by A3, and all of that is r. So that is why we call it the common ratio. A is the first term. Again, that happens when r raised to the n is 1, in which case whatever the exponent is would have to be 0, so that we have the first term. So how do I determine whether a given sequence is in geometric progression? Well, I take my A2 divided by A1, A3 divided by A2, and if all of that is the same, then that is my common ratio. I find the first term, and then I write the general formula, either starting from 0 or starting from 1. Then I can predict what A394 is, i.e. the 394th term. Okay, so use this to determine if a given sequence is a geometric progression and hence find specific terms of the sequence. Now, you could also have this question where you're given the first term and the common ratio, and you're asked to find the first 50 terms of the sequence. That's very easy because that will be the formula. If I'm already given the first term and the common ratio, all I need to do is plug in n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, and that will give me all the terms, as many as I want. Same thing here, as many as I want. Same thing here, as many as I want. But what if I started off by giving you the sequence and then ask you to find the 50th term? You take negative 1 divided by 1, 1 divided by negative 1, negative 1 divided by 1. You realize that each time you get the answer negative 1. So that is my common ratio. My first term is A. Get the general term, and you're done. Okay? We'll see another example later. But before we get there, let's look at arithmetic progression. An arithmetic progression is a sequence of the form A plus D, A plus 2D, ellipsis, A plus ND, plus, plus, plus. Or let me just define it in general. An arithmetic progression is a sequence where the term in n is an equals a plus n times d. In this case, n goes from 0, 1, 2, 3, and so on and so forth. So the first term will be a0 or a0, and that will just be a. Then the next term, and the next term, and the next term. Or if I'm going to start from 1, 2, 3, then the term in n, an, is going to be a plus n minus 1d. And when n is 1, I have 1 minus 1, that is 0. So the first term will be a1, which is a. Okay? A is known as the initial term, and d is the common difference. So how do I know to find d? Well, just subtract consecutive terms. So we have here that a2 minus a1 must be the same as a3 minus a2, must be the same as a4 minus a3, and all of that would be d. That is our common difference. So, summary. If you are given an arbitrary sequence and you want to determine whether it's a GP or an AP, there are a couple of things you do. First of all, number one, locate the first term, A, not D. Delete that and put A. So locate the first term, A. So whether it's a GP or an AP, the first term is going to be A. And number two, check if it has a common ratio R or a common difference. So try taking the quotient of consecutive terms and see what you get. If it doesn't make sense, then we are probably not in a GP. Then now take the difference between consecutive terms, and if it makes sense, then that means we have a common difference. If it doesn't make sense, it means that the sequence is probably not an AP, it's not a GP, it may be a recurrence sequence or something else which we have not yet seen in this class at least. Next, if we determine that there is a common ratio or a common difference, then we can write the general term an of the sequence, and then we can go ahead and find specific terms, e.g. 207th term of the sequence. Again, as we did before, if you are already given the first term and the common difference, you can list out as many elements as possible. All you have to do is, that is your first term plus n times the common difference, and just go from 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, 5, and that gives you as many terms as you desire. Arithmetic progression, geometric progression. Let's take a slight detour here and talk about strings in a few seconds. A string is a finite sequence of characters from a finite set, the alphabet. Okay, so sequences of characters or bits are important in computer science. If it is an empty string, we represent it by lambda. And if it is not empty, for example, the string A, B, C, D, E has length 5. So we would leave that for computer science measures or when we are dealing with applications in computer science, but I would like to go back into our study of sequences. Recurrent sequences or recurrence relations. Since we have not treated relations formally, I would prefer to just stay with the word sequences. So, recurrence sequences. A recurrence relation or a recurrence sequence, AN, is an equation that expresses AN in terms of one or more of the previous terms of the sequence. A0 right up to AN minus 1. Now, to quickly make that very simple and understandable, this is what I'm talking about. AN is our sequence, but the term in N is defined as AN equals AN minus 1 plus 3. N goes from 1, 2, 3, 4, and then there is an initial condition, A0 equals 2. Without the initial condition, there's not much you can do. You need an initial condition. So realize that AN is defined in terms of a previous term, AN minus 1. So this is a recurrence sequence or a recurrence relation, and it must always have an initial condition. Once that is given, once AN is defined and the initial condition is defined, we can then ask you to find A1, A2, A3, A4. In this case, A1 would be A0 plus 3, and A0 is 2, so that's easy. And A2 is going to be A1 plus 3. We know what A1 is, you plug it in. A3 would be A2 plus 3. We know what A2 is, you plug it in. That is known as a recurrence relation. Of course, the most important or the most famous occurrence sequence or relation is a Fibonacci sequence, and we would be looking at that also. On our way to the Fibonacci sequence, we can look at this. AN, the sequence is defined as AN equals AN minus 1 minus AN minus 2. So we define the entire term in N in terms of two previous terms. That's interesting. And that runs for N equals 2, 3, 4, and so on and so forth. You cannot go very far without initial conditions, because all I know is AN equals AN minus 1 minus AN minus 2. So what is A1? I don't know. What is A2? What is A0? So you need initial conditions. In this case, your initial conditions are A0 is 3 and A1 is 5. So that makes life really, really easy. And we start from 2, which means I cannot say A1. A1 has already been defined. So what would A2 be? A2 would be A1 minus A0. We know what A1 is. We know what A0 is. What would be A5? A5 is going to be A4 minus A3, and so on and so forth. Okay, now let's go on to the mother of all recurrent sequences or relations, the Fibonacci sequence. Define the Fibonacci sequence as follows. The initial conditions are F0 is 0, F1 is 1, and the term in N is Fn minus 1 plus Fn minus 2. So if you were to remember this very easily, the nth term in a Fibonacci sequence, or the term in N, is simply the sum of the two directly preceding terms. So Fn equals Fn minus 1 plus Fn minus 2. So it's very easy to tell what the next term would be, with the initial conditions that F0 is 0 and F1 is 1. I'm not sure what you've heard about the Fibonacci sequence, but I would ask you to read a little bit and see how it came about, the whole story of rabbits in an enclosure. It's beautiful. Also think about the golden ratio. Have you ever heard of the golden ratio and how it relates to the Fibonacci sequence? Read a little bit about that and we will talk about it in class. Again, once we have this formula with the initial conditions, we can get as many terms as possible. But this is something I want you to do as a math nerd. The next time you're eating peanuts or popcorn from the same bag with a friend, why don't you guys do Fibo snacks? Kind of eat the popcorn following the Fibonacci sequence, and at the end of the day, try to figure out who ate more. That would be interesting. So at the start, nobody takes anything. That is F0. Then the first person takes one popcorn, just one grain. The next person, F2, takes one. Then the next person takes 1 plus 1, which is 2. Then the next person takes 1 plus 2, which is 3. The next person takes 2 plus 3, which is 5. The next person takes 8. And you guys just keep eating, following the Fibonacci sequence and call it Fibo snacks. At the end of the day, when the bag is empty, you guys can sit down and figure out who ate more. And then probably the next time you are with somebody, you may want to either start first or second, depending on who ends up eating the most number of popcorns or peanuts. Okay, that's Fibo snacks for you. You could even do Fibo nachos. I actually saw this somewhere in the joke column, where you have these two little nerds were eating nachos and they decided to use Fibo nachos. You take one nacho, the other person takes one, then you take 2, then you take 3, then you take 5, then you take 8, and see how far you'll go before you run out of nachos, and then figure out who ate the most, and you can call that Fibo nachos. And whatever it is you are eating, you could call it Fibo P for Fibo peanuts or whatever it is. But it's just exciting to see how Fibonacci sequence really plays in real life situations. As a matter of fact, there is a lot of correlation among things that exist in nature with the Fibonacci sequence. Read a little bit about that and we'll talk about it in class. Okay, let's proceed. Solving recurrence relations. First of all, we find a formula for the nth term of the sequence, or like I prefer to call it, the term in n, generated by recurrence relation. And if that is done, that is called solving the recurrence relation. Such a formula is a closed formula. There are various methods for solving recurrence relations, and some will be covered in chapter 8, so we cannot go into depth right now. And also, we can actually guess what the formula could be, and then we would use mathematical induction to prove it. Again, that is in chapter 5. So you can see that there are a couple of things we would not be able to do in this section because we have to either bring in chapter 5 or bring in chapter 8. Here's an iterative solution example. Working upward, forward substitution. Let an be a sequence that satisfies the recurrence relation an equals an minus 1 plus 3 for n equals 2, 3, 4. And the initial condition is that a1 is 2. So I start off, I look for a2, a3, a4, and then I use that to determine by guesswork what the term in n would be. So an equals an minus 1 plus 3, but from the way I look at things, I have a2, that will be 2 plus 3. I have a3, that will be 2 plus 3 plus 3. I have a4, that will be 2 plus 2 times 3 plus 3. Just follow that and I'm able to determine that my an minus 1 is going to be 2 plus 3 parenthesis n minus 2 plus 3, and I reduce that down to 2 plus 3 into n minus 1. So this is what we mean by solving a recurrence relation or a recurrence sequence. I write the sequence just in terms of n without the an minus 1. Then if I want you to find a25th, all you have to do is plug 25th in and that gives you a25. Otherwise, you'll be forced to get all the terms before you can find a308 or a9024. Let's see a different method to do this. Iterative solution example. Again, our sequence an is an minus 1 plus 3 and our initial condition a1 is 2. So here we're looking at downward, backward substitution. So I just proceed very slowly. An is an minus 1 plus 3. But what is an minus 1? An minus 1 is an minus 2 plus 3 plus 3. And then what is an minus 2? So I do my downward, backward substitution and then figure out by guesswork that I'll end up with 2 plus 3 into n minus 2, which is a1 plus 3 plus 3 into n minus 2, which is 2 plus 3 into n minus 1. And then we can use mathematical induction to verify this. But do not expect me to give you so many of these in class yet, because we have not yet looked at mathematical induction, nor have we looked at chapter 8. Here's a very simple financial application. You can actually do this in business. Suppose that a person deposits $10,000 in a savings account at a bank yielding 11% per year. That's huge. I wish I found such a bank. With interest compounded annually, how much will be the account after 3 years? And the reason why we're using math in this case and PN is because we really want to make it exciting. You can do this using knowledge from business without applying recurrent sequences. But if you apply recurrent sequences, we can actually determine what the person's yield is going to be after 100 years. If the person lived to be 100 after the deposit was made, all we have to do is write PN. PN would be the 100 year. So P100 would be the 100 year. So all I have to do is come up with a recurrent sequence, which will be of the form Pn equals Pn minus 1 plus 0.11 Pn minus 1, which is just 1.11 Pn minus 1. And the initial condition is that P0 is 10,000. So it's very easy for me to determine what the savings would be in 3 years, in 4 years, in 25 years from the date or the year the money was deposited. Of course, I have to reduce this. I have to solve it and actually get p to the n minus 1 just in terms of n. And if we do forward substitution or backward substitution, as we have seen, we would end up with Pn equals 1.11 p to the n minus 1, which is 1.11 raised to the power n times p0, which is 1.11 raised to the power n times 10,000. So now if I want to find what the savings would be or what the total amount in the account would be in 25 years, I just put my 25 here and use a very simple calculator, and I can tell what would happen. In 30 years, it's going to be 228,992.97. Special integer sequences. As I mentioned before, a sequence could be AP, arithmetic progression, GP, geometric progression, recurrent sequence, or none of the above, just a special integer sequence. So given a few terms of a sequence, try to identify the sequence. So we have to conjecture a formula. Some questions to ask. Are there repeated terms of the same value? Can you obtain a term from the previous term by adding an amount or multiplying by an amount? Can you obtain a term by combining the previous terms in some way? Are there cycles among the terms? Do the terms match those of a well-known sequence? So you put all of these together and then come up with a formula. We will look at several examples in class, and you should be able to figure out the nth term of various sequences whose first couple of terms are given. Let's look at some examples. Example 1, find the formula for this sequence right here: 1, 1/2, 1/4, 1/8, 1/16. So the first thing you want to do, of course, the initial term. You got that? Okay. So try subtracting consecutive terms. So do 1/2 minus 1, do 1/4 minus 1/2, 1/8 minus 1/4. I don't seem to have a common difference. AP out the window. It cannot be arithmetic progression. Try dividing. 1/2 divided by 1, that is 1/2. 1/4 divided by 1/2. In a minute, that seems to be 1/2. Let's try again. 1/8 divided by 1/4, that is 1/2. 1/16 divided by 1/8, that's 1/2. Oh, wait a minute. It has a common ratio. The common ratio is R, so that is a geometric progression. So therefore, my term in n, an, is just 1 divided by 2 to the n, and that's it, starting from 0. Now I can find the 378th term if I want to. What about the second one? If I look at these, I have 1, 3, 5, 7, 9. Okay, let's see. Let's try to divide consecutive terms. 3 divided by 1, that is 3. 5 divided by 3, that is not 3. So out the window, it cannot be a geometric progression. Let's try arithmetic progression. 3 minus 1, that is 2. 5 minus 3, that is 2. 7 minus that is 2. Oh, wait a minute. There is a common difference. D equals 2, and the first term is 1. So that is an arithmetic progression, and we can write that as an equals 2n plus 1. And you can find whatever term you want. And then I look at this. I try subtraction. It doesn't work. I try division. Oh, wait a minute. I realize that the common ratio is -1. The first term is 1, so that is a geometric progression, and so on and so forth. And there are sequences again that would not be either of the three that we've seen: AP, GP, recurrent. Here are some very useful sequences: n squared, n cubed, n to the 4, 2 to the n, 3 to the n factorial, and fibo. We would come back to this when we look at summations. Summations. This will be part 2 of our lecture on sequences and summations, section 2.4. So part 1 comes to an end right here. And if you have any questions, you can send it to me by email. You can write it on the comment section on YouTube, or you can ask me in class. Thank you very much. God bless you, and see you in section 2.4, sequences and summation part 2.